Hi all, welcome back to the second lecture on quantum mechanics. So in the last class, we have just introduced what is the state in quantum mechanics, what is the main difference between the classical and quantum. And today we are going to discuss what is the interpretation, what is the main difference between the classical physics and quantum physics in terms of its interpretation. Okay. Now we can just revise what we have discussed in the last class. So in last class we have said that in classical physics the state of the system is defined in terms of position momentum. So if you just know the position x and momentum p, then simply the doublet xp defines the state of the system. Whereas in quantum mechanics, that is not possible. In quantum mechanics, the state is defined in terms of wave function, and wave function mathematically expressed as psi, and which is a function of x and t in general, and it can be a function of p and t as well. Now, the surprise is there is no direct meaning for this wave function. The wave function is interpreted in terms of its mod square. So the mod square is called the probability density, is interpreted as probability density. So what it is mean? So it means that if you integrate mod psi square between two positions, if you integrate it over between two positions, then this will give the probability to find the particle between the position A and B. Okay, so let us plot some the wave function. So this is y-axis or vertical axis. This is the horizontal axis, and we have some wave function is of the form like this. Okay, now let us mark the position A and B. Suppose this position is A and this position is B. So if you integrate mod psi square, so this is mod psi square. So if you integrate this function between A and B, so that is basically the area under this curve. So that will give the probability to find the particle between these two positions. So what it actually means, so that its meaning is we already discussed earlier. So if you perform the same experiment for large number of times for the same system, then probabilistically between A and B, the probability to find the particle between A and B will be this much. So that means if you use some numbers, so let this integral is equal to 0.4. That means if you perform 1,000 times or 10,000 times the same experiment, and you can see that the particle is will be in between the position A and B for 40% of times. So if you perform the experiment for 10,000 times, then almost 40% means almost 4,000 times the particle will be between A and B. Okay, so the particle can be anywhere in each of the experiments. So it sometimes it may be here, or it may be here, it may be here, it may be here. So it is possible to take any position in each measurement. But on the average, between A and B, we'll get around 40%. So there is the meaning of this result. So this is a statistical interpretation. So this thing we have already discussed in the last class, and today what we are going to discuss is, so suppose if you consider one of such experiment. So in one of such experiment, the particle will take one particular position. Suppose, okay, for the example, suppose the particle is taking the position C. Okay, so in one particular experiment, I found that the particle is in position C. Then my question is, what would be its position just before the measurement? So what would be the position just before the measurement? So what is the answer for it? So in quantum mechanically, there are many possibilities. Okay. In classical physics, there is only one possibility. We can clearly find out what is the position of the particle just before the measurement. So obviously, it will be almost close to C. So if it is a classical particle, and if I found that it is at position C at some moment, then just before looking the particle, it would be at very close to that same point only. It may not be at some other point. Okay. So if it is a classical particle on measurement, suppose if I found it is in position C, then just before the measurement it will be very close to C. It cannot be here or it cannot be here. Okay, it would be very close to C. So quantum mechanically, what is the answer? So what was the position of the particle just before the measurement? So there are basically two different point of view. So not only two, there are many point of views. So I am just focusing only two of them because it is really important for our next course of discussion. So there are many different point of view. So the one of the two of this point of view is, one is a realistic viewpoint, and another one is orthodox viewpoint. So the realistic viewpoint is put forward by Einstein and his followers. So according to its theory, according to its viewpoint, it says that it must be very close to C, or it must be at the position C just before the measurement. The only problem is the quantum mechanics that we know, the formulation of quantum mechanics that we have already developed as of now is incomplete. So that is why we could not able to predict its position as C just before the measurement. And he is for the Einstein and his followers introduced a new theory called hidden variable theory. That is the variable that we are using in the particular the present quantum mechanics is incomplete. So if you could able to find a few more variables, then it is possible to locate the particle just before the measurement itself. And that theory is called hidden variable theory. So it is just an hypothesis. It has not formulated anything. It's just an hypothesis. So there is a one point of view. There is the particle might be at the position C just before the measurement. So so this is a case. I'll just rewrite again. So this is point A, this is point B, and this is point C. Okay. So on measuring the on checking the particle, while observing the particle, I found that the particle is at position C. So according to the Einstein viewpoint, it must be at position C immediate just before the measurement. Now, what is the orthodox viewpoint? It is exactly opposite viewpoint. The orthodox viewpoint is put forward by the Bohr and followers, and according to their viewpoint, the particle, we cannot say the position of the particle just before the measurement. It can be anywhere. It can be at A, or it can be at B, or it can be here, maybe D, or it can be here at E. It can be anywhere. it, we cannot say it is at C. Now what happens is, while observing the particle, or while measuring the position of the particle, the wave function. So initially we have drawn some wave function for this particle. Now this function will collapse. So if you are getting the position as C, this is A, this is B, then instead of this wave function, the wave function will become like this. It will become a sharp peak with origin at C. It's like a Dirac delta function. Okay, so this kind of process is called the wave function collapse. So we don't know how to mathematize this collapse. So we don't have any mathematical formulation to explain this collapse. But this orthodox viewpoint gives a satisfactory explanation in some manner that the wave function must be changing its shape, and it is taking a single location, and it is getting a very large peak at single position if it is taking a if it is taking if you are trying to locate the position of the particle. Okay, now what happens after that? So after the measurement, this drag delta function will again evolve with time according to the Schrodinger equation. So after the collapse, so this is collapse. So after the collapse, the wave function of the particle will again evolve. So it might be taking some other shape. Okay, so if we again measure, it will might be taking some other position, maybe some position T, and it will take peak around this point. So according to the orthodox viewpoint, there are two kind of process. One is the evolution according to the Schrodinger equation. So between the measurement, the wave function will evolve according to the time dependent Schrodinger equation, and during the measurement, it will collapse. If you are trying to find the location, or if you are trying to find the momentum of the particle, it will collapse to is one of the eigenstate. So it will be a Dirac delta function, suppose in case of position. Okay, so these two are the two different point of view. So at one point in the realistic viewpoint, it was exactly at the same location just before the measurement. But the orthodox viewpoint says that it can be anywhere. It can be anywhere before the measurement, and only during the measurement it is taking one single position. Actually, there are many dialogues between Einstein and Bohr regarding this, the interpretation of the result of quantum mechanics, and that introduced many new phenomena and many new the physical phenomenons there is one paradox called Einstein-Podolsky-Rosen paradox, which is connected with the phenomena called entanglement. So the many beautiful physics has come forward due to this the difference of opinion between this orthodox team and realistic team. Okay, so it has happened. All this discussion happened before 1950s, and after 1950, one scientist Bell, John Bell, proposed an experiment. So you might have heard about the Bell's inequality. So in 1964, he proposed an experiment to disprove this hidden variable theory, to disprove that Einstein's viewpoint. And that experiment is conducted by the John Clauser in 1972 and Alan Aspect in 1982. They used the photons to perform such experiments, and they found they proved that Bell's inequality, and which actually implies the hidden variable theory is not correct. So with that those experiment, the orthodox approach got more strengthened, and nowadays this orthodox approach is very acceptable viewpoint. Now, not only that, there are many other viewpoints, depending upon the scale of the quantum mechanics that you're using. The people are trying to use the various viewpoint in order to understand the physics behind this quantum process. Okay, and this John Clauser and Aline Aspect recently received Nobel Prize on their work of the proving of Bell's inequality. So that's all for now. So in this section, we have just introduced uh, the, the various viewpoint on the results of quantum mechanics. So we know that the quantum mechanics is a probabilistic physics, and even though it is probabilistic, there is we can uh, we can have some mathematical result, and this mathematical result has to be interpreted, and there are many ways to interpret it, and we have discussed two of them, the realistic viewpoint and the orthodox viewpoint, and we said that this orthodox viewpoint is more correct, and it has more followers than this realistic viewpoint. Now this hidden variable theory is experimentally, the hidden variable theory is wrong now. It is There is no there is no experimental background for this realistic viewpoint, and orthodox viewpoint is now supported by the experiment introduced by this Bell, John Bell. Okay, so that's all for now, and in the next class we'll start with the time independence from the equation and stationary states. Okay, so thanks for watching. See you later.